Hi, everybody. I'm James Dreeler from the WWF, and I'm presenting a bit of work that integrates work both of my own, but principally of a couple of researchers, Dougal Harris and Cosmin Burles, and it's under the GEF Sustainable Land Management Program, together with some partners on the screen there. And what we're looking at here is how to try ultimately to reduce the costs and increase returns to landowners from carbon offsets within the thicket, but obviously thereby to try and kickstart real restoration at the landscape level. So the area that we're working in as part of the SLM is within the Bavianes Cliff farming area. So that's within the nature reserve. There's a central area. I'm sure many of you are familiar with it. It's typical spectrum thicket, and we had Jan Vlok come through to identify the particular areas that are viable for this. However, though that's a pilot site, what we're really talking about is facilitating restoration across the thicket. And we've been talking about this for years. Of the two projects that are currently registered, one is private sector and one is public sector, and neither of them have gone through a verification process, which is where they actually independently assess the carbon that's been sequestered in the landscape and pay out offsets. And so both of those have now lapsed. And that means that we don't have any good examples of it paying out. And obviously that's led to a lot of landowner skepticism. We know we have high costs. The returns are very contingent on a number of factors. And if you're a landowner, you also have opportunity costs of not using that land while you're waiting for it to pay out. So we're not really making much progress. So an interesting thing to do was to look at where we might be able to influence some of those costs and risks and reduce the costs or the returns to the landowner. We built a simple model in Lumina Analytica, a spreadsheet-based modeling software, taking data from field operators, measurements, literature estimates where there weren't any, just to try and see where best we could apply our knowledge. And for each of these sort of cost and return things, we had to look at a large number of components. Some of them are contingent on the area, some of them are not, and all of them looking at a typical 20-year model, which is a 20-year project is quite long, but that's in the realm of a standard carbon project. So bearing in mind that a lot of the costs are estimated, one of the interesting outcomes here is to see how much of the total return from carbon is eaten up and how much of it returns to the landowner. If we look at the national carbon tax price of 120 Rand a ton, what we can see is that up to 81% of all of the returns are swallowed up by costs, and only 19% of that goes to a landowner. But at a typical sale price under that of 100 Rand a ton, the return to the landowner is only 1% of the entire carbon cost. So neither of those obviously is a very attractive option for a landowner. And in fact, if we annualize those returns, what you see is roughly 250 Rand a hectare per year for a landowner under 120 Rand a ton, or only 30 Rand a hectare a year if you're looking at 100 Rand a ton. So obviously the price is critical. And if you then look at over the full 20 years here, for a 1,000 hectare project, you're probably going to get an internal rate of return of under 2%. If you're a developer, you really want to get at least 10%. And you can look here, this gap between the blue, that's our return, the red is just pure cost. And if you're looking at your investment, your rate of return here, that is a significant gap at 120 Rand a ton. And in fact, if you push the carbon price up to 430 Rand a ton, well, then you're making your internal rate of return. It then becomes very attractive. But the price of carbon is outside of our ability to influence. It's dictated by a lot of different market factors, And it is something that is increasing at the moment, and we anticipate it to go up after a long lull. But that's not something that we can change. So increasing the price of carbon increases our returns. And you can see a linear correlation here in this graph. The different lines refer to the different quantification of soil carbon. So obviously, the more of the carbon that's sequestered within the environment that you can claim, the better your return. But the UNFCCC standard methodology, that's the AR ACM 0003, tends to give us a much lower estimated soil carbon return. The tier 1 is using their standard estimate, and that blue line is as much as you would be able to get. If we use localized measures, we run up against a problem that the methodology says there is a maximum amount that you can claim for soil carbon regardless, and that's a conservative estimate. That's our green line there. And actually, what we've seen within the literature is we should be able to claim soil carbon sequestration up to the yellow line there. The challenge is in actually doing it. So represented here differently, the blue bar on the left is all of the above ground carbon, the root carbon, and the litter carbon. And that comes to as much as 221 tons of carbon dioxide, or 221 offset units over a 20-year period. The tier 1 soil cap, that's the UNFCCC standard estimate, would give us another 17 tons per hectare over the period, and using the localized estimate would give us another 42 tons, which is a significant amount. However, accessing that last 44 tons, that's the total amount, would require actual in-field estimate and measurement of the carbon, and that tends to be very expensive. So much so that actually it's not worth claiming for that at present, because the in-field estimates become too costly. So where can we influence our costs? Obviously, rehabilitation is our key cost. And that is an area where a lot of work has been done. You'll have seen Yondella Norman's presentation earlier, looking at different ways of doing rehabilitation to increase our return success and to reduce costs. The validation itself is something that is outside of our hands. It's largely because we have international validators. And should a local market develop for carbon within the thicket, we'll probably see validators, local validators coming up and reducing that cost. So scale helps that one. The project management is up to the project itself. We estimated the standard 5% for this, but it's obviously very contingent on who's doing it. And the initiation costs are fairly standardized because there's just a minimum amount of time you need to do to develop a project document and to go through the whole process. So the real opportunity is within the monitoring processes, that monitoring, reporting, and verification. But just quickly on that initiation, we estimate currently for CDM or Vera project that your project development will be in the realm of 720 to R1 million. Nesting a number of different activities or a number of projects within a program of activities will reduce the per project development cost by up to 370,000 Rand. And if we had a national standard, it could drive it down even further, but that is dependent on the Department of Mineral Resources and Energy approving a national standard, which is certainly not happening now and may happen sometime in the distant future. So monitoring costs are where it's at. The soil carbon you could do remotely. Our main costs for soil carbon are using the in-field costs. You have to go and sample. But then there's a lot of sort of post-field processing in order to do your laboratory analysis. And you have to archive those samples for the long term. And so all of that has costs associated with it. So to access that last section of the soil carbon becomes tricky. Bayer developed a remote sensing approach to assess soil carbon with fairly good correlates up to 40% cover within the thicket. And so that is a possibility, at least for the earlier stages in the process as you're accumulating soil carbon. You can do a remote sensed assessment. And so we thought perhaps the remote sensing approach for above ground carbon would be a similarly cost-reducing approach. Because again, for that, the main costs are field assessment and our biodiversity. So this is just an oversight of the project. The background is a digital surface model, and we'll talk about how we developed that. But what we have here are in red are severely degraded areas, in yellow moderately degraded areas, and in green is intact thickets. And we needed to sample in all of these in order to calibrate the model to see if we could detect kind of the carbon growth. And so within all of these areas, we allocated random sample sites, and the little X's are ground control points. I'll talk a little bit more on that shortly. Just a quick oversight of the degradation classes. We have at the bottom right, that's more or less intact thicket within the Bavianskloof. You can see it doesn't have as high a tree component as other parts of thicket, but this is typical of the Bavianskloof spectrum thicket. In the middle, we have moderate levels of degradation, and on the right, we have severely degraded thickets. Field work was carried out by Cosmin Bolus, and we had different sized plots depending on the thicket conditions. As I'm sure you're aware, intact thicket is very hard to penetrate and has a very high plant density. So for those plots, we used a 10 meter by 10 meter plot. For the moderate and severely degraded, we used 20 by 20 meters, often because there was less vegetation present. Spatial accuracy is obviously critical when we're doing remote sensing. So we used a digital GPS, and also with post-processing, we're able to get it down to approximately a 30 centimeter accuracy for each of the control points. Those are the corners of our boxes. And we used a nested 5 by 5 meter subplot for assessment of tree size. And within these areas, we were measuring our plant height, our canopy width, and our canopy length to get an area of canopy. And these are variables that were used for allometric assessment, the equations from Van der Feefer and Cowling in 2019. And we used those allometric measures to determine the carbon within the area. Just important, two things to notice. All of the brush under 50 centimeters was not measured. After our first few samples, we assessed that the value in terms of the carbon was very small for the small brush, and the difficulty in sampling meant that the cost went up significantly. And another thing is that the litter, because we didn't want to disturb the plots, we assessed it outside, but within a standard distance of the plots themselves. So the outcome from that carbon assessment, we had, as you can see, clearly increasing carbon stocks from degraded to moderately degraded to intact thicket. And the standard errors are fairly reasonable, although higher in the litter, and we'll talk on that a little later. But it's also important to note also that the estimates of the carbon, the standing carbon, are within the ranges that we've seen from other areas where we've had carbon sampling. So we're fairly confident that they're a good basis for our remote sensing work. So a quick overview of that remote sensing approach. Having established our carbon stocks, we then had to calibrate our images to make sure that they were spatially accurate, correcting for geometric and atmospheric effects. And we had to decide which features were most useful for our model, and that was on the basis of their error. We'll touch on that. But we then fitted and tested the regression model to establish an estimate of the above ground carbon from the spatial imagery. In terms of imagery, we built a digital surface model from an aerial mosaic from the National Geospatial Information Service. That's a 0.5 meter 4-band stereo taken from aircraft overflights and is freely available. For the features, we used WorldView 3 high-resolution imagery. Now, this is a satellite product at a very high resolution, 0.34 meters, with 8 bands ranging from the visible all the way through to far infrared. To enable the orthorectification and the correction of all of the imagery, we had to establish 30 ground control points using that same digital GPS and post-processing them to a very high level of accuracy. And then atmospheric correction and pan sharpening was also done using off-the-shelf software. I won't go into too much detail about the per pixel features we use, but typical vegetation indices plus the ratios between the individual bands, as well as then averaging those across the sites to give us per plot features. And then we could extract also data such as the mean, the entropy, and the standard deviation of each of those per pixel characteristics. So in the total, we had 522 different features to look at. The features used for the model then were selected on the basis of the root mean of square errors, and it was a stepwise automated feature selection. Each one of them was added on to see how much it improved the model, and then the one that improved it the most at each stage was selected. And in order to prevent overfitting, we also monitored this the root mean of square errors. And once it started overfitting, we went back and used the number of features that gave us the best fit. So in this case, we had 15 features. And you can see that very first feature, the logarithm of the red band over the panchromatic band, actually gave us on its own a very, very good fit. But it was improved gradually by each of the features. And what does the model give us in terms of accuracy? Well, if you look at the measured above ground carbon on A and B, that's on the x-axis, and the predicted on the y, you can see very good correlations, 0.886 for the multivariate analysis, that's using all 15 of the features, but actually 0.851 with just the first feature, that's our R over the panchromatic, the red over the panchromatic. So this model, the second one, actually is by far the simplest, much less computationally intensive, and actually gives us a very good R squared, certainly sufficient for inclusion in the key carbon methodology, that's the AR-ACM 0003 under the clean development mechanism, which is the one that is used for our Thicket biome. There are sources of error. The litter sampling was very noisy, and after a little bit of analysis, we decided that probably the sample size is too small, given the heterogeneity of the thicket. We probably need much larger litter samples. And obviously, at 40% of the above ground carbon, that's a significant thing to ensure that we get correct. So that is something that we'd recommend going forward. Also, the remote sensing is insensitive to vegetation height. So the areas that had the biggest differences, the individual plots, also were home to the second biggest tree. But we didn't see that across the entire data set. There wasn't a significant skewing or error related to vegetation height. And so here we have a derived above ground carbon map for the entire area. The circles and the associated squares there are center period irrigation and agriculture. And so those obviously would not be part of the assessment and likely will be misestimated. But for the thicket itself, we have fairly good correlates. So critically, what does this mean in terms of costs? Well, we still have a significant portion of the cost being our in-field expertise for the ground truthing, but we have much less of that, and it's replaced to some extent by software and imagery. Software that was developed has been open sourced by Google. It's available for anybody. The link is here and will be provided elsewhere. The imagery itself, the WorldView 3 imagery, is actually quite expensive, but compared to the amount of field assessment is significantly cheaper. But what we also did is tested it against other imagery. So Google ran this model using the WorldView 3 August 2017 imagery, which is in the center of that table. Across the top of the training imagery, and across the side is the assessment. And you can see we have fairly good correlates across the board, including the NGI imagery, which is actually the 4-band aerial imagery, which is available for free. So in other words, we can use cheaper imagery and possibly drone imagery to reduce the cost further. So obviously, this model was built on a single site and is accurate for that site. The question may be whether it's applicable to the broader thicket biome as a whole. But the advantage here is that we don't have a single product. What we actually have is a methodology and software that enables you to run and test your accuracy for any other site. And on the back of that, we developed this model calibrated for a coarser resolution Landsat 8 imagery, so that's just standard Landsat 30-meter resolution for the whole of the thicket. And this product is available online. You can have a look at it. Again, this is a much broader estimate, and we haven't done field work for the whole of it, but it's certainly for the Landsat data within our sample area, it's fairly accurate. So we feel like it should be broadly applicable, and welcome further inputs on it, and would really like to see other people rolling it out in other areas if possible, so we can see the accuracy. I'd just like to thank Cosman Bolas, who did the bulk of the field work, which is arduous and backbreaking, and Dougal, who did all of the methodological development and the tool itself, and for making it available. So we hope that going forward, this method will enable reduction in costs for carbon projects and help get us closer to getting good returns for landowners and actually doing the restoration we need to do.